Okay, we discussed reactions of various orders and methods to determine order of a reaction. Okay, what are the various methods we have to determine order of a reaction? We have 5 methods. We have integration method. In integration method, what we follow? Integration method, we follow integral form of rate equations. At various intervals of time, we calculate some data like remaining concentration of reactant or product concentration, Tx A minus x. That data we have to calculate. That data we have to substitute integral form of rate equations. The equation which gives constant value of K, that gives order of reaction. Next, half-life method. In half-life method, what is the formula? 1 plus log T1 by T2 by log A1. Antena? Okay. By using this equation, if half-life versus initial concentration data is given, we can calculate order of a reaction. Okay. Next, graphical method. In graphical method, we follow A minus x versus time graphs. Okay. For different order reactions, different graphs we have. The general expression is 1 by A minus x whole power n minus 1 is equal to n minus 1 knt plus 1 by a power n minus 1, but this is not applicable to first order kinetics. So this is the general expression we follow. Okay, 1 by a minus x whole power n minus 1 versus t. If you are getting straight line, that corresponds to nth order reaction. In the case of first order reaction, we follow this one. Ln a minus x is equal to minus k1t plus ln a. So ln a minus x versus t, if you are getting straight line, that corresponds to first order reaction. This is graphical method. Okay, fourth one, differential method we follow. So in that we use the differential form of rate equation. We calculate rate of reaction at different concentrations of reactant. Okay, and finally how to get any order of a reaction? Log R2 by R1 by log C2 by C1. So this gives order of reaction. Okay, we follow which rates and initial rates are rates after sometimes generally. Generally we follow initial rates. After mixing reactants, immediately we take readings. Okay, we calculate rate since no formation of product, no reverse reaction. So that's why we follow initial rates. Okay, and lastly, Oswald isolation method. When we follow Oswald isolation method, if more than one reactant, many reactants are there, we follow Oswald isolation method. Okay, in Oswald isolation method, for example, if you have A, B, C reactants, if you want to calculate order with respect to A, what we have to follow? We have to take B and C in excess amount, right? Okay, those are the various methods to determine order of a reaction. Still from JL syllabus, we have steady state approximation, collision theory, transition state theory, and complex reactions. Even complex reactions not mentioned, but if you see previous papers, they have given some questions. So that also we have to discuss. Though only 4 topics we have mainly: steady state approximation, collision theory, transition state theory, and complex reactions. Okay. So mostly it may be completed today. Okay. Complete Jada, right? Next one, steady state approximation. Steady state approximation or steady state principle and steady state principle. Steady state approximation or steady state principle, SSP. Okay, if you have a complex reaction, how we get rate equation? And to get rate equation, we proceed with respect to slow step or rate determining step. So rate equation can be obtained. Okay, rate equation can be obtained with respect to slow step. Okay, In the case of complex reactions, rate equation can be obtained by proceeding with respect to slow step or rate determining step. In the case of complex reactions, rate equation can be obtained by proceeding with respect to slow step. For example, for a complex reaction, we have more than one slow step. For example, we have more than one slow step, or slow step is unknown to us, not known to us. For example, for a complex reaction, if more than one step is slow step, or if slow step is not known to us, in such case what we have to follow? In such case, how to get rate equation? Okay, in such case rate equation can be obtained. In such case, rate equation can be obtained. In such case, rate equation can be obtained by following. In such case, rate equation can be obtained by following steady state approximation or steady state principle. Okay, if more than one step is slow step, or slow step is not mentioned in the given mechanism, they have not mentioned slow step. Which is slow step? That is not mentioned. In such cases, we follow steady state approximation. Generally, we follow with respect to product formation step. And in this case, with respect to which step we follow? With respect to product formation step we follow. Okay, and later we see examples also. Now, what is steady state approximation? According to steady state approximation, the change in the concentration of intermediate with the time is 0. The change in the concentration of intermediate with the time is 0. The change in the concentration of intermediate with the time is 0. Okay, nothing but the concentration of intermediate remains constant during reaction. The change in the concentration of intermediate with the time 0 means what? During the reaction, is there any change in the concentration of intermediate or no change in the concentration? Intermediate. No change in the concentration of intermediate. The concentration of intermediate remains constant. The concentration of intermediate remains constant during reaction. The concentration of intermediate remains constant during reaction. Okay, the change in the concentration of intermediate with time is 0, or the concentration of intermediate remains constant during the reaction, or the rate of formation of intermediate is equal to rate of formation of intermediate is equal to rate of destruction of intermediate or consumption of intermediate. Rate of formation and rate of destruction both are same. Rate of formation of intermediate is equal to rate of consumption of intermediate according to steady state principle. For example, for a reaction, we have mechanism like this, and A gives rise to intermediate, gives rise to product. A gives rise to intermediate, gives rise to product. So, according to steady state approximation, what? The rate of formation of intermediate and its consumption can be taken as same. Okay. So, therefore, our concentration, intermediate concentration remains constant with the time. So, therefore, the change in the concentration of intermediate with the time is equal to what? And 0. The change in the concentration of intermediate with the time is equal to 0. For example, if you have two intermediates, then the change in the concentration of I1 with the time, the change in the concentration of I2 also with the time is equal to 0. Okay. Next one, when steady state approximation is valid and when steady state approximation is not valid. In which cases we can apply steady state approximation and in which cases we cannot apply steady state approximation. If you see, for example, I am taking this reaction, A gives rise to, I gives rise to product P or some B, A gives rise to I gives rise to B. Let us consider the rate constant for formation of intermediate is I1, rate constant for consumption of I is I2. Rate constant for formation of I is K1 and rate constant for consumption of I is K2. For example, if K1 is many times more compared to K2, if K1 is many times more compared to K2, that means the rate of formation of intermediate is many times more compared to its consumption. Okay, as fast as it formed, with the same speed it is not undergoing in reaction, or with the same speed it is not consuming. Okay, with which speed I is forming, with the same speed it is consuming, or with the same speed it is not consuming, not consuming. In such cases, what happens if you see, if you plot a graph between concentration versus time, if you plot a graph between concentration versus time, for concentration of A decreases with the time, concentration of A decreases with the time, concentration of B also increases with time. Later we will discuss in detail about these reactions only. Okay, kinetics also will discuss later. Concentration of B increases with time, and especially if you concentrate on I, here concentration of I increases, okay, accumulation of I is observed. Since as fast as it is forming, with same speed it is not consuming, so that means accumulation of I takes place. So the concentration of I increases, reaches a maximum value, after that it decreases, and this is the expression for concentration of I we will get. With the same speed it is not consuming, so therefore accumulation of I is observed. I value reaches a maximum value, after that it decreases. Okay, I participates in a reaction after some time only. Such a time is called as induction period. After a certain period only, I participates in the reaction, so the concentration of I decreases. That is called induction period. Now, in this case, if you observe whether concentration of I is maintained constant or not maintained constant, concentration of I is maintained constant or not maintained constant, not maintained constant, increased finally reaches a maximum value, again decreased. So in such cases steady state approximation is not valid. In such cases steady state approximation is not valid. So when steady state approximation is not valid, if K1 is many times more compared to K2, in such cases steady state approximation is not valid. But if K2 is many times more compared to K1, if K2 is many times more compared to K1, so as fast as I formed, immediately it participates in the consumed, okay, reaction. Okay. So in such cases, if you plot a graph between concentration versus time, okay, concentration of reactant decreases exponentially, and for concentration of B we will get this type of plot, and for I we will get a graph like this, and concentration of intermediate we will get a graph like this. In the beginning, small increase in the concentration is observed, small increase in the concentration is observed, and as fast as it formed it will be consumed. So its concentration is maintained very low and almost constant. Its concentration is maintained very low and almost constant. So in this case steady state approximation is valid. So you just remember this condition. What is the condition? And if K1 many times more compared to K2, SSA is not applicable. If K2 is many times more compared to K1, in such case steady state approximation is valid. And what is steady state approximation? You remember the change in the concentration of intermediate with the time is equal to 0. Intermediate concentration remains constant. What is differentiation of constant? And 0. Differentiation of constant is 0. So di by dt is equal to 0. So you remember these 3 points. Okay. Once a question given in CSIR for 2 marks, A gives rise to, I gives rise to B, K1, K2, okay, if steady state approximation is applied on I, if steady state approximation is applied on I, A gives rise to, I gives rise to B, if steady state approximation is applied on I, what is the concentration of I? if steady state approximation is applied on I, what is the concentration of I? 0. Change in the concentration is 0. Concentration of I is not 0. Concentration of I is not 0. Okay. Change in the concentration is 0 with the time. Okay. Okay. Steady state approximation can be applied on I, that is given. So according to steady state approximation, the change in the concentration of intermediate with the time is equal to 0. The change in the concentration of intermediate with the time is equal to 0. Okay, the change in the concentration of intermediate with time means, okay, we have to see net change in the concentration of I, net change in the concentration of I with the time. Okay, in the first step, whether I is forming or consuming, and forming, I is forming, so plus sign we will get. With which rate it is forming, and rate means what? Rate constant into concentration of reactant. Rate is equal to what? Rate constant into concentration of reactant. What is rate constant? K1. Concentration of reactant, that is A. In the second step, whether I is forming or consuming, and consuming. So which sign we will get? Minus sign. Minus sign will get. With which rate it is consuming? Rate constant into concentration of reactant. Rate constant is K2, concentration of reactant, that is I. Only 2 steps are there. In those 2 steps I is involved. Net change is equal to what? 0. According to steady state approximation, net change is 0. Now you take the expression for I and so K1 into I is A is equal to K2 into I. So the expression for I is equal to K1 into A by K2. So this is the expression for concentration of I. K1 into concentration of A by K2. So already we entered into complex reactions, and it is a elementary reaction or complex reaction? Complex reaction. It is a more than one step reaction. Okay, steady state approximation we follow for complex reactions only, right? Right. For example, I am giving some mechanism like this, and A plus A, some A star plus A star gives rise to products. Rate constants I am giving K1, K minus 1, K2, where A star is intermediate. A star is intermediate. I am giving some mechanism for this is the reaction, and A gives rise to products. This is the mechanism I am giving. A gives rise to products. The mechanism is like this. A plus A gives rise to A star plus A star gives rise to product where A star is intermediate. Okay, then what is the concentration of A star? What is the expression for concentration of A star according to steady state approximation? What is the expression for concentration of A star according to steady state approximation? Now, according to steady state approximation, what we have? The change in the concentration of intermediate with the time is equal to 0. The change in the concentration of A star with time is equal to 0. The change in the concentration of A star with time is equal to 0. Okay. Now, where A star is involved? In the forward reaction, A star is involved. In the backward reaction also A star is involved. In the second step also A star is involved. In the forward reaction, whether A star is forming or consuming it? Forming. So which sign will get? Plus sign. With which rate it is forming it? K1 into rate constant into concentration of reactants. That is concentration of A into concentration of A. That is concentration of A square. K1 into A square. And in the backward reaction, A star is consuming or forming it? A star is consuming. With which rate it is consuming it? K minus 1 into rate constant into concentration of reactants. What are the reactants in backward reaction? A star and A. The reactants in backward reaction, that is A star and A. Next, in the second step, also A star is involved, whether A star is forming or consuming. A star is consuming, so minus sign. With which rate it is consuming? K2 into A star, that is equal to 0. So like this we have to write it. Once a question given in DL, some mechanism is given, H2Br2 reaction mechanism is given, how to get Br concentration, Br intermediate, bromine intermediate concentration. Okay, similarly we have to follow. Okay, and now here K1 into A square is equal to, if you bring these to right side and take A star common, both becomes positive, and if you take A star common, the remaining terms are K minus 1 into A plus K2, K minus 1 into A plus K2. Finally, the expression for A star is equal to K1 into A square by K minus 1 into A plus K2. This is the expression for A star. K1 into A square by K minus 1 into A plus K2. Okay. Generally while we are following steady state approximation, directly we can write like this, and concentration of intermediate is equal to rate equation for formation of intermediate, by sum of rate equations for consumption of iron. Directly we can write like this, sum of rate equations for consumption of I except concentration of I. Okay. See, in this case, if you see in the numerator what we are writing, K1 into A. What is K1 into A? K1 into A is nothing but rate of formation of intermediate, or not? Yes, K1 into A is rate of formation of intermediate. Here K1 into A square we are writing in the numerator. What is K1 into A square? K1 into A square is nothing but what? Rate of formation of A star. K1 into A square is rate of formation of A star. Right? Right. In the denominator what we have to write? Sum of rate equations for consumption of I. Here where I is consuming, and the second step I is consuming. Okay, sum of rate equations, and that is K2 into I. K2 into I, except I we have to write, since we are taking equation for I only. So we get K2. And then next, in this case if you see where A star is consuming, in the backward reaction A star consuming, the second reaction also A star is consuming. So therefore K minus 1 into A, except A star we have to write K minus 1 into A plus next K2 into A star we cannot write, so plus K2. Directly you can write like that. So this is useful later in photochemistry also. We follow steady state approximation. Right. This is the concept of steady state approximation. Okay, now? Next one, important for all competitive exams, that is Lindemann's theory of unimolecular reactions. Lindemann's theory of unimolecular reactions. Lindemann's theory of unimolecular reactions, important, and in JL especially we may expect one question from Lindemann's theory. Okay. In CSR also repeatedly they are giving questions from Lindemann's theory, 4 marks questions they are giving sometimes. Okay. So unimolecular reactions, what are unimolecular reactions? If activated complex, okay, actually we have not discussed the transition state theory, there we will get about activated complex. Okay, if you have energy profile diagram, here highest energy occupied by what? Activated complex and okay, reactant to convert reactant into products, initially it forms what? Activated complex. Activated complex further breaks to give products. Okay, in detail we will get in the next topic. Okay, if activated complex contains single activated reactant molecule, if activated complex contains single activated reactant molecule, if activated complex contains single activated reactant molecule, then it is called unimolecular reaction. If activated complex contains single activated reactant molecule, then it is called unimolecular reaction. For example, we have A and A. This is A star. This activated complex contains how many molecules? Only one molecule and activated molecule, that is activated molecule. So if activated complex contains only single activated molecule, that is called a unimolecular reaction. We have various theories for unimolecular reactions. Okay, the various theories for unimolecular reactions. Out of all those theories, this is the basis for all theories. This Lindemann theory is the basis for all modern theories. This is the basis for all modern theories of unimolecular reactions. This is the basis for all modern theories of unimolecular reactions. Lindemann theory is the basis for all modern theories of unimolecular reactions. Okay, now I am taking a unimolecular reaction. Consider a reaction like this. A gives rise to product. Consider a reaction like this. A gives rise to product. Now, what is the mechanism proposed by Lindemann? If you see that mechanism proposed by Lindemann is like this. A plus A, just now whatever the second example we discussed, that is nothing but mechanism of unimolecular reactions. A plus A gives A star plus A, next one A star gives product. Here the rate constant for forward reaction K1, backward reaction K minus 1, and for second step K2. So this is the mechanism proposed by Lindemann. Okay, whenever two A molecules undergo collision, exchange of energy takes place. Exchange of energy takes place. This A molecule may give some energy to A. So we get A star plus A. This is called as, this A star is called as energized molecule. Energized molecule. Okay, as it gains some energy from this A, okay, this A star may be considered as energized molecule. So this collision is called as elastic collision or inelastic collision. This collision is called as inelastic collision. Inelastic collision means what? Before and after collision, if kinetic energy remains the same, that is called what? Elastic collision. Before and after collision, if kinetic energies are different, that is called inelastic collisions. So kinetic energy may be converted to some other form of energy. Okay, if kinetic energy may be converted to heat energy, kinetic energy may be converted to vibrational energy. Okay, so then such collisions are called as inelastic collisions. Okay, before and after the collision, if kinetic energy remains same, that is called elastic collisions. After collision, okay, if kinetic energy changes, if kinetic energy is converted to some other form of energy like heat energy or vibrational energy, then such collisions are called what as inelastic collisions. So here in inelastic collision, energized molecule will get, that is vibrationally excited molecule will get. We get vibrationally excited molecule will get. Its vibrational energy increases. Some of kinetic energy may be converted to what? Vibrational energy. This question given and in TS Genco chemist. In TS Genco chemist exam, this question given. Okay, based on that concept question given. Okay. This is the vibrationally excited molecule we are getting, or energized molecule we are getting. Since kinetic energy converted to vibrational energy, this is called an elastic collision. So now this participates in a unimolecular reaction to give product. This is the mechanism proposed. And now we don't know slow step. We don't know slow step or rate determining step. In such cases, generally we proceed with respect to product formation step, and we proceed with respect to what? Product formation step. So if you write rate of product formation, if you write rate of product formation, that is V is equal to, in which step product formation is occurring? And second step. Rate of product formation is nothing but second step rate. What is second step rate? K2 into A star. Second step rate is K2 into A star. Let us consider that is equation 1. Rate of product formation is nothing but rate of second step, rate constant into concentration of reactant. But what is A star here? But what is A star here? Whether it is reactant or product or intermediate? Intermediate. A star is intermediate. But A star is intermediate. But A star is equal to intermediate. So its concentration can be obtained by, what? Steady state approximation. So by using steady state approximation, what we get? Concentrations of unstable intermediates we can calculate. By using steady state approximation, we can calculate concentrations of unstable intermediates. So its concentration can be obtained by steady state approximation. Now if you apply steady state approximation, what we get? Directly tell me. Okay. In the second derivation we did, or what we have to write in the numerator, rate of its formation, where A star is forming, the forward reaction A star is forming. So K1 into A, K1 into A square, that is the rate of formation of A star, and in the denominator we have to write where A star is consuming. The backward reaction A star is consuming, so we get K minus 1 into A. Other than A star we have to write K minus 1 into A plus, second step also A star is consuming, so K2, right. So K1 into A star by K minus 1 into A plus K2, that is the concentration of intermediate. So sometimes they may ask you to give the expression for concentration of intermediate. Okay. Now if you substitute in 1, so from 1 we get V is equal to K2 into A star, concentration of A star, that is K1 into concentration of A power 2 by K minus 1 into A plus K2. So this is the rate equation proposed by Lindemann for unimolecular reactions. This is the rate equation proposed by Lindemann for unimolecular reactions. Just we proceeded with the product formation step, K2 into A star. What is concentration of A star? That we got by using steady state approximation, that we substituted, and then K2 K1 A square by K minus 1 into A plus K2. This is the rate equation proposed by Lindemann. For the reactions involving gases, for the reaction involving gases, unimolecular gas phase reactions, if you take unimolecular gas phase reactions, if you consider, in such case we replace concentration term by pressure term. K2 K1 PA power 2 by K minus 1 into PA plus K2. For the reactions involving gases, we replace concentration term by pressure term. Now we have two cases. One is, what is the kinetics of unimolecular reactions at high concentration of intermediate and low concentration of intermediate, reactant, at low concentration of A, and at high concentration of A. Let us consider this is equation 2. Let us consider that is equation 2. At low concentration of A, if you see in the denominator we have K minus 1 into A plus K2, K minus 1 into A plus K2. At low concentration, K minus 1 into A value is less compared to K2 or not? Yes. So K minus 1 into A can be neglected compared to K2. So K minus 1 into A plus K2 we can write as K2. So from 2 we get V is equal to K2 K1 A square by K2. So K2 gets cancelled. The denominator we can write as K2. K minus 1 into A can be neglected. So V is proportional to what we are getting at A power 2. So therefore, at low concentration of reactant, unimolecular reactions follows which order kinetics and second order kinetics. So write that point. Therefore, at low concentration of reactant, at low concentrations of reactant, at low concentrations of reactant, unimolecular reactions follow, second order kinetics. At low concentrations of reactant, unimolecular reactions follow second order kinetics. If you take gases, for the reactions involving gases, we say at low pressure, and at low pressure this term is negligible. At low pressure this term is negligible. So we get what? Pa power 2 second order kinetics. At low pressure unimolecular reactions follow second order kinetics, and for the reactions involving gases. Almost in all competitive exams these questions given, and at low pressure what is the order, at high pressure what is the order. Recently also given in CSR for 4 marks. Okay. Next one, at high concentration of A. Second case, at high concentration of A. Before that you write one more point. At low concentration of A. If you see here, K minus 1 into A is dominating over, K2 is dominating over K minus 1 into A or not? Yes, K2 is dominating over K minus 1 into A. So this we can write like this or not. On both sides I am multiplying with A star. On both sides I am multiplying with A star. Okay. On both sides I multiplied with A star. This is nothing but what? K2 into A star is nothing but what? K2 into A star is nothing but rate of product formation. What about this K minus 1 into A star? K minus 1 into A star. This is nothing but rate of backward reaction. Rate of backward reaction, or that is also called as deactivation step. And forward reaction is called as activation step. Forward reaction is called activation step. Backward reaction is called as deactivation step. The another name is de-energization step. De-energization step. Here this A star is energized, activated. That's why the forward reaction is called activation step. Whereas in the backward reaction, again A star is deactivated. In the backward reaction, so that is called deactivation or de-energization step. Activation step, deactivation or de-energization step. Okay, so therefore K minus 1 into A star is nothing but what? K minus 1 into A star is nothing but rate of deactivation step. That means if rate of product formation step is more compared to rate of de-energization step, then unimolecular reactions follow second order kinetics. Okay, like that also we can verify it. At low concentration of A we can say, or if rate of product formation is more, compared to rate of de-energization or rate of deactivation, then unimolecular reactions follow second order kinetics. Write that point. If rate of product formation is more, compared to, if rate of product formation is more compared to rate of de-energization, if rate of product formation is more compared to rate of de-energization, then unimolecular reactions follow, second order kinetics. Right, now write at high concentration of A. At high concentration of A. Now which is negligible and at high concentration of A, K2 is negligible compared to K minus 1 into A. So we get K minus 1 into A, that if you substitute in equation 2, V is equal to K2 K1 A square by K minus 1 into A. So concentration of A gets cancelled. So that is equal to K2 K1 by K minus 1 into concentration of A. Okay, now high concentration, so therefore compared to K minus 1 into A, K2 can be neglected, so that we substituted in equation 2, AA gets cancelled, we got K2 K1 by K minus 1 into A. Now unimolecular reactions follow which order kinetics and at high concentration? What we are getting? Concentration power 1. They follow first order kinetics, or at high concentrations or at high pressures. For the reactions involving gases, at high pressures, unimolecular reactions follow first order kinetics. Okay. At high concentration of A or at high pressures, unimolecular reactions follow first order kinetics. At high pressures or at high concentration of reactant, unimolecular reactions follow first order kinetics. Next, if you see here, K2 constant, K1 constant, K minus 1 also constant. So all these constants I am indicating as K infinity. Why I will explain later. So V is equal to K infinity into A we are getting. So first order kinetics, where K infinity is nothing but what? K2 K1 by K minus 1 we are taking as K infinity. K2 K1 by K minus 1 we are taking as K infinity. And now which step is dominating and here? Rate of product formation or rate of deactivation step? Rate of deactivation step. See here K minus 1 is into A is dominating over K2. So if K minus 1 into A into on both sides I am multiplying with A star, and both sides I am multiplying with A star. This is nothing but what? Rate of deactivation step. This is nothing but rate of product formation step. So if rate of deactivation step is more, compared to rate of product formation, then unimolecular reactions follow first order kinetics. And write that point. If rate of deactivation is more, compared to rate of product formation, if rate of deactivation is more compared to rate of product formation, then unimolecular reactions follow, first order kinetics. Okay, next one, we are taking a particular situation, that is previously we considered rate of product formation is more compared to deactivation. Now we considered rate of deactivation is more compared to rate of product formation. Now we are taking a particular situation, both occurs at same rate. Okay, consider a particular situation where rate of deactivation step and rate of product formation step both are same, both are occurring at same rate. Now consider a particular situation, that rate of product formation is equal to rate of deactivation. Consider a particular situation that rate of product formation is equal to rate of deactivation, and let it happens at concentration of A is equal to A of. Let it happens at concentration of A is equal to A of. Okay, at which concentration this situation may observe that concentration of reactant we are taking as A of. Now rate of product formation. What is rate of product formation? K2 into A star. That is equal to rate of deactivation. That is K minus 1 into A into A star. Rate of deactivation is K1 minus 1 into A into A star. What about the concentration of A at that situation? A of. The concentration of A at that situation we are taking as A of. So A star gets cancelled. So it is indicated as A of, since if you see the mechanism, from the forward reaction, let us consider we are getting 100 A star molecules. From the forward reaction, how many A star molecules we are getting? 100 A star molecules we are getting. Now rate of deactivation and rate of product formation both are same. That means 50 are participated in the backward reaction, 50 are participated in the product formation. 50 are participated in the backward reaction, 50 are participated in the product formation. That means the rate of formation of product is, for the formation of product, how much probability we have? Only 50% probability we have. Okay, for the formation of product we have only 50% probability. That's why that concentration is indicated as A of n. Okay. Now if you take A of n, at which concentration we will get this situation? At which concentration we will get this situation? So K2 by K minus 1. A of is equal to K2 by K minus 1, or K2 by K minus 1 we can write as from this. But we have K infinity is equal to K2 K1 by K minus 1. From this K2 by K minus 1 we can write as K infinity by K1. K2 by K minus 1 we can write as K infinity by K1. Okay, so A of is equal to K infinity by K1. Once this question given and in CSR for 4 marks, what is the expression for A of or K1? Or K1, if you take expression for K1, K infinity by A of. Okay, Randy. Okay, we discussed 3 cases, and product formation is more compared to deactivation. Deactivation is more compared to product formation, and both occurs at a same rate. Okay. At which concentration of A we are getting this situation, that we are indicating as A of, and we also derived the expression for A of, that is nothing but K infinity by K1. Okay. Right, at this situation, what about the probability for product formation? 50% only. Write that point. At this situation, comma, the probability for product formation is, at this situation, the probability for product formation is, 50% only. At this situation, the probability for product formation is 50% only. So therefore, rate of reaction at this situation is nothing but half of previous rated. Rate at this situation is nothing but what? Rate of product formation is nothing but half of previous rate expression. Right? Next one, Andy. Next we have rate equation like this. Rate equation we got V is equal to K1 K2 A square by K1 K2 A square by K minus 1 into A plus K2. We got the rate equation like this. Okay, this I am writing like this only. K1 K2 concentration of A by K minus 1 into A plus K2 into concentration of A. K1 K2 A by K minus 1 into A plus K2 into A. Okay, another some special case is given, that is okay, right, let K dash is first order rate constant, let K dash is first order rate constant under any condition, let K dash is first order rate constant under any condition. Under any condition means whatever may be the concentration, high concentration or low concentration. What we are taking, let K dash is the first order rate constant under any condition, whether it may be high concentration of reactant or low concentration of reactant. If K dash is the first order rate constant, then rate equation we can give like this. Rate is equal to rate constant. Rate constant is what? K dash, okay, concentration of A power what we get? 1, first order rate constant we are taking. Then rate equation we get rate is equal to rate V is equal to K dash into A power 1. Now if you compare these two, then what is the expression for first order rate constant? And from these two equations, okay, from the above two equations we get the expression for K dash as VV gets cancelled and VV gets cancelled, AA gets cancelled. Okay, VV gets cancelled, AA gets cancelled. So in the place of K dash what we have? In the place of K dash we have K1 K2 A by K minus 1 into A plus K2. K1 K2 into concentration of A by K minus 1 into A plus K2. So this is the expression for first order rate constant under any conditions. Previously, what is the conclusion we got? At high concentration or low concentration, it followed first order kinetics. Once you check, high concentration, ante kada. If you apply this to high concentration, for example, if you high concentration first order, antena? Okay. High concentration apply cheste raadu. Okay. K1 K2 ante right. High concentration apply cheste AA gets cancel అయిపోతుంది, AA gets cancel అయిపోయి K1 K2 by K minus 1 వస్తుంది. అక్కడ కూడా అంతే వచ్చింది కదండి, రేట్ కాన్స్టెంట్ K1 K2 by K minus 1, right? Same we will get it. Okay, if you apply at high concentration, this K2 is negligible. AA gets cancelled, K1 K2 by K minus 1 will get. There also we got rate constant same, K1 K2 by K minus 1. Okay, so from this, if you plot a graph between K dash first order rate constant versus concentration of A, if you plot a graph between first order rate constant versus concentration of A, we will get a graph like this. We will get a graph like this, hyperbola graph we will get. So with increase in concentration of A, first order rate constant also increases, and at very high concentrations what happens, and these two gets cancelled, this is negligible. At very high concentrations K2 is negligible, these two gets cancelled. So K dash reaches a constant and maximum value. That is nothing but K1 K2 by K minus 1, that we consider as K infinity. That's why K1 K2 by K minus 1 considered as K infinity. At very high concentrations, first order rate constant reaches a maximum value. That maximum value is nothing but K infinity. So let us consider this is equation 3. Equation 3. Now if you take inverse of equation 3, I am taking it. Reverse of equation 3. Okay. Then we get 1 by K dash is equal to K minus 1 into A, by what we get, K1 K2 concentration of A plus K2 by K1 K2 concentration of A. we are taking inverse of equation 3. Okay, k minus 1 into a by k1 k2 a plus k2 by k1 k2 into a. Now k2 k2 gets cancelled, a gets cancelled. So 1 by k dash is equal to, what about k1 k2 by k minus 1 and k1 k2 by k minus 1 is nothing but k infinity. So reverse we have k minus 1 by k1 k2 we have, so therefore we get 1 by k infinity plus 1 by k1 into 1 by concentration of A, 1 by k1 into 1 by concentration of A. So this equation gives how first order rate constant changes with concentration of reactant, how first order rate constant changes with the concentration of reactant. This is non-linear relationship we have, this is linear relationship we have. This is the non-linear relation we got between first order rate constant and concentration of A. So this is in the form of y is equal to C plus mx. This is in the form of y is equal to C plus mx. So if you plot a graph between 1 by k dash versus 1 by concentration of A, we have to get straight line. If you are getting straight line, it indicates that it follows Lindemann's mechanism. If you are not getting straight line, it indicates it doesn't follow Lindemann's mechanism. Okay, if it follows Lindemann's mechanism, we will get a straight line like this, where slope is equal to what? 1 by k1 and intercept is equal to 1 by k infinity. 1 by k infinity. What is the expression for A of only? Once you check. Expression for A of is equal to what we have? K infinity by k1. Then expression for A of the concentration at which the rate of deactivation step and rate of product formation step becomes the same. This is the formula we have, k infinity by k1. So how to get k infinity by k1 from slope and intercept data? Slope by intercept. If you do by intercept, this k infinity we get numerator. So concentration of A of is nothing but what? Slope by intercept. So from this graph we can calculate where rate of product formation and rate of deactivation step becomes same, at which concentration. Okay, and we considered another situation, that is k dash is rate constant under all conditions, that means it may be low concentration or high concentration. So then we compared these two. Okay, in the place of k dash we got this equation. Based on this k dash versus concentration of A, if you plot a graph, you will get a hyperbola type of graph. So k dash increases with the concentration of A and reaches a constant value at very high concentrations. At very high concentrations, k2 is negligible, these two gets cancelled. So k1 k2 by k minus 1, that is nothing but we consider as k infinity. Okay, and we took inverse of this equation. Now we got a linear relationship between first order rate constant and concentration of reactant. This is the linear relationship we have. From that, slope is 1 by k1, intercept 1 by k infinity. From this slope and intercept also we can calculate A of. Okay, and lastly, let k1 dash and k2 dash, let k1 dash and k2 dash are, let k1 dash and k2 dash are first order rate constants. Let k1 dash and k2 dash are first order rate constants at concentrations of reactant, A1 and A2, at concentrations of reactant A1 and A2 respectively. Let k1 dash and k2 dash are first order rate constants at concentrations of reactant A1 and A2 respectively. So this equation, if you apply at two concentrations, okay, from this graph we can get at two concentrations or not. This is at 1 by A1 concentration, this is at what? 1 by A2 concentration. What we get here? 1 by k1 dash. This is what? 1 by k2 dash. So k1 dash, k2 dash values we will get at A1 and A2 concentrations respectively. So that if you apply in this equation, let us consider this is 4. So from 4 we can write first at K1 dash, A1 concentration, at A1 concentration if we apply 1 by K1 dash is equal to 1 by K infinity plus 1 by K1 into 1 by concentration of A1. And if you apply at A2 concentration, we get 1 by K2 dash is equal to 1 by K infinity plus 1 by K1 into 1 by concentration of A2. Let us consider this is equation 5 and this is equation 6. We applied this equation at two different concentrations, A1, A2 concentrations. The corresponding first order rate constants we consider as K1 dash, K2 dash. Now if you do 6 minus 5, we get 1 by K2 dash minus 1 by K2 dash minus 1 by K1 dash is equal to 1 by K infinity, 1 by K infinity gets cancelled. Now what is common, and 1 by K1 is common, we get 1 by concentration of A2 minus 1 by concentration of A1. Once a question given in CSIR for 4 marks, and they have given K1 dash, K2 dash value and A1, A2. Which data is given, and A1, A2, K1 dash, K2 dash, that data is given. Okay, that data is given. They ask you to calculate rate constant for activation step. Rate constant for activation step. What is activation step, Andi? What is activation step? Forward reaction is the activation step. Rate constant for activation step means what we have to calculate? K1 we have to calculate. We can calculate K1 or not? Yes. If these 4 data are available, we can calculate K1. So they ask you to calculate K1. Okay. Next one we have for gas phase reactions. If you see, V is equal to, we have what? K1 K2 Pa square by K minus 1 into Pa plus K2. K1 K2 Pa square by K minus 1 into Pa plus K2 we have. Now previously we discussed at low pressure it follows which order kinetics, and at high pressure, at low pressure it follows second order kinetics, and at high pressure it follows first order kinetics, right? Now at which pressure it changes its order? At which pressure it changes its order? Okay, let us consider we are moving from low pressure to high pressure. We are moving from low pressure to high pressure. We are increasing the pressure of reactant. At low pressure it follows which order kinetics? Second order kinetics. At high pressure it follows first order kinetics. Let us consider at a particular pressure, at this pressure, this is called a transition pressure. At this transition pressure, let us consider it changed its order from second order to first order. Okay, we are changing pressure. Okay, we are moving from low pressure to high pressure. At low pressure it follows second order kinetics, at high pressure it follows first order kinetics. At a particular pressure, that is transition pressure, let it change from second order kinetics to first order kinetics. Now this transition pressure we want to calculate. This transition pressure we want to calculate. So if you see at this pressure, second order kinetics and first order kinetics becomes same. At this pressure the rate equations for second order kinetics and first order kinetics are same. So at a transition pressure, we have second order kinetics means K2 into Pa square, first order kinetics means K1 into Pa square. This is second order rate constant, this is first order rate constant. Okay, Pa. So, one PA gets cancelled, and so PA is equal to, transition pressure is equal to K1 by K2. So, this is the expression for transition pressure of A. So, they may give you first order rate constant and second order rate constant. They may ask you to calculate transition pressure. So, transition pressure is nothing but simply ratio of first order rate constant to second order rate constant. Ratio of first order rate constant to second order rate constant gives transition pressure. And finally, some examples if you see for unimolecular reactions. The examples for unimolecular reactions are generally decomposition reactions and isomerization reactions. Decomposition reactions and isomerization reactions are examples for unimolecular reactions. Decomposition reactions and isomerization reactions are the examples for unimolecular reactions. For example, decomposition of butane to give 2 moles of methane, decomposition of dimethyl ether gives CH4 plus H2 plus CO. Isomerization of methyl cyanide to methyl isocyanide, decomposition of ethyl amine. So, these are the examples given in books. Okay, these are some examples given. So, decomposition reactions and isomerization reactions are examples for unimolecular reactions. Okay, so mainly you remember those points. What is the concentration of intermediate? What is the final rate equation? At high concentration it follows second order kinetics. At low first order kinetics. At low concentration it follows second order kinetics. Next, first order kinetics, rate of product formation or deionization. That relation you have to verify. Okay. Next, what is the expression for A of? What is the expression for A of? K infinity by K1. K1 is called what? Rate constant for activation step. Rate constant for activation step. K minus 1 is rate constant for deactivation step. K2 is rate constant for product formation step. Okay. So next, this is some questions based on Lindemann's theory. And see, yes, sir, this is given. What is the expression for K1? That is also given a direct question. K1, the expression for K1 is K infinity by A of. Okay. Next one, the first order rate constant. The first order rate constant. The first order rate constant for a unimolecular gas phase reaction. The first order rate constant for a unimolecular gas phase reaction. Gas phase reaction A2P, the first order rate constant for a unimolecular gas phase reaction A2P that follows Lindemann's mechanism, that follows Lindemann mechanism, that follows Lindemann mechanism is 2.0 second inverse, is 2.0 second inverse at PA is equal to 1 atmosphere, at PA is equal to 1 atmosphere, and 4.0 second inverse, and 4.0 second inverse at PA is equal to 2 atmosphere, and 4.0 second inverse at PA is equal to 2 atmosphere, at PA is equal to 2 atmosphere. the rate constant for the activation step is, the rate constant for the activation step is, all the data is given, K1, K2, instead of concentrations of reactants, what is given? Pressure is given. Gas phase reaction, it is gas phase reaction that is mentioned. So that's why instead of concentrations, pressure is given. What is the equation? Last equation we have to use. What is the last equation we got? 1 by K2 dash minus 1 by K1 dash, that is equal to 1 by K1, this is the rate constant for activation step, by 1 by concentration of A2. In the place of concentration of A2, what we have to use? PA2 minus 1 by PA1. So substitution only. 1 by K2 dash 4 minus 1 by K1 dash 2, 1 by K1, 1 by PA2 1 by 2 minus 1 by 1. So here LCM is 4. Antena? 4, 1 minus 2 and minus 1, that is equal to 1 by K1, 1 by 2 minus 1 minus 1 by 2. So minus minus gets cancelled. So we are getting K1 is equal to 2 by 4. Sorry, K1 is equal to 4 by 2. That is we are getting 2 and K1 is equal to we are getting 2. This is also previous CSR question given for 4 marks. Right, K uni is the effective first order rate constant, is the effective first order rate constant, is the effective first order rate constant of the following unimolecular reaction. K uni is the effective first order rate constant of the following unimolecular reaction: A plus M K1 K minus 1 A star plus M, A star gives rise to product. K uni is the effective first order rate constant of the following unimolecular reaction. Same mechanism given, just in the place of A what is given? M is given. Okay, continuation. The slope and intercept of the plot of 1 by K uni versus 1 by concentration of A. The slope and intercept of the plot of 1 by K uni versus 1 by concentration of A are 4 into 10 power 6, 4 into 10 power 6 and 8 into 10 power 11. 4 into 10 power 6 and 8 into 10 power 11. The value of K minus 1 by K2 is, the value of K minus 1 by K2 is, let's check how to get K minus 1 by K2 from slope and intercept. What is the equation we have? 1 by first order rate constant versus 1 by concentration of A. Linear relationship. Once you check linear relationship, this is the equation we have. Antena? Right? That is the linear relationship we have. This is in the form of y is equal to C plus mx. C is equal to 1 by K infinity, or 1 by K infinity is nothing but what? Inverse of K infinity. What is inverse of K infinity? K1 K2 by k minus 1, okay na, right. Slope k1. Now what we want to calculate, and k minus 1 by k2. How to get k minus 1 by k2? And k minus 1 we want to get to numerator, that means slope by intercept. Slope is k1, 1 by intercept means k minus 1 by k1 k2. So k1 k2, so k1 k1 gets cancelled. So k minus 1 by k2 is nothing but what? Slope by intercept. Slope is given 4 into 10 power 6, intercept is given 8 into 10 power 11. So 4 ones are 4 twos are 0.5 into 10 power minus 5. So that is 5 into 10 power minus 6, and 5 into 10 power minus 6. That is the value of k minus 1 by k2. That is the ratio of rate constant for deactivation step to rate constant for product formation step. Slope by intercept, intercept by slope అండి చూడండి. ఇది కరెక్టేగా, 1 by k infinity కరెక్టేనా? రాంగ్ చెప్పారు మీరు. k minus 1 by అన్నిసార్లు అడుగుతున్నారు, ఎప్పుడైందండి మరి? అరే k1 into intercept by slope we have to do. So k minus 1 by k2. So k minus 1 by k2 is nothing but intercept by slope. Intercept given 8 into 10 power 11. Slope is given 4 into 10 power 6. So that is 2 into 10 power 5. So 2 into 10 power 5. Right. Next one, Andy. Right. For the following reaction, A plus B I gives rise to product. For the following reaction A plus B, okay, reverse reaction I gives product. K1 is equal to 10 power 5 liter per mole per second, K minus 1 is equal to 10 power 4 second inverse, K2 is equal to 10 second inverse. For the following reaction, that is the reaction given, corresponding rate constants given, K1, K minus 1 and K2. Continuation. The steady state approximation can be applied. The steady state approximation can be applied. The steady state approximation can be applied on concentration of I. The steady state approximation can be applied on concentration of I. Continuation, comma. The steady state approximation can be applied on concentration of I, comma. The observed rate constant of product formation will be, the observed rate constant of product formation will be, the observed rate constant of product formation will be. So we can apply steady state approximation to I. Okay. And now V is equal to what? And rate of product formation. Okay, V is equal rate of product formation is nothing but rate constant into concentration of reactant in that step, that is K2 into I. So V is equal to K2 into, how to write concentration of I directly? How we can write concentration of I directly? In which step I is forming andi? In the forward reaction I is forming, so rate of forward reaction K1 into A into B. K1 into concentration of A into concentration of B. Next, in the backward reaction I is consuming, so the rate of backward reaction is K minus 1 into I, other than I we have to write K minus 1 plus, in the second step also I is consuming, the rate of consumption of I is K2 into I, other than I we have to write, that is K2. So overall what we are getting, and V is equal to K2 K1 by K minus 1 plus K2 into A into B. Okay, what is the overall rate constant we got, Andy? This is the overall rate constant we got. What is the overall rate constant? K1 K2 by K minus 1 plus K2. This is called as what? Observed rate constant. Okay, the rate equation is equal to what we get, and V is proportional to what? A into B. V is proportional to A into B. If you remove the proportion, whatever the constant we get, that is called rate constant. What is the observed rate constant? This is the observed rate constant. So K observed is equal to K1 K2 by K minus 1 plus K2. Now substitute the data given. Okay, first we proceeded with respect to product formation step, and concentration of intermediate we wrote based on steady state approximation. Okay, in the numerator rate of formation of intermediate, that is K1 into A into B. In the denominator consumption K minus 1 into I and K2 into I, other than I we have to write K minus 1 plus K2. So observed rate constant is equal to K1 10 power 5 into K2 10 by K minus 1 10 power 4 plus K2, that is 10. This is the 10,000, 10 power 4, this is a 10, and almost 10 can be neglected compared to 10,000. So nearly, if you calculate 10 power 6 we are getting here, 10 power 6 by 10 power 4. So nearly we will get 100, and around 100 we will get, right? This 10 may be neglected compared to 10,000. Okay, next one. Okay. Next, write this reaction. This is also previous CSR question given for 2 marks. Experimentally determined rate law. Experimentally determined rate law. Experimentally determined rate law. Experimentally determined rate law for the chemical reaction. For the chemical reaction 2NO2F. 2NO2F gives rise to 2NO2 plus F2. Experimentally determined rate law for the chemical reaction 2NO2F gives rise to 2NO2 plus F2 is R is equal to K into NO2F. R is equal to K into NO2F, comma, the rate determining step consistent with rate law is, options 2NO2F gives rise to 2NO2 plus F2. NO2F gives rise to NO2 plus F. NO2 plus F gives rise to NO2F. NO2F plus F gives rise to NO2 plus F2. Which mechanism consistent with rate law? Which one is the slow step, rate determining step? Which may be rate determining step only from the options? First one, First one endukandi? Rate, what is the rate equation? Rate is equal to K into NO2F. That means in the rate determining step, the reactant should be NO2F. In the rate determining step, the reactant should be NO2F. Where we have NO2F only? Second option, right? If it is the rate determining step, we get rate is equal to rate constant into NO2F power 2 we will get. If this is the rate determining step, what is the rate equation we may get? Rate is equal to rate constant into NO2 into F. If it is the rate determining step, we will get rate is equal to rate constant into NO2F into F. Okay, direct question. Next one, the decomposition mechanism of ozone is the decomposition mechanism of ozone is right O3 O2 plus O3 in equilibrium with O2 plus O K1 K minus 1. The decomposition mechanism of ozone is comma O3 plus O gives rise to 2O2 K2 continuation. If K minus 1 into O2 is less than, if K minus 1 into O2 is less than K2 into O3, if K minus 1 into O2 is less than K2 into O3, then the order of the reaction with respect to ozone is, options 0, 1, 2, complex, like that options given. What is the order with respect to ozone? Apply chesna? Guess. Okay, you may follow with respect to product formation step, and which is slow step, which is fast step, that is not mentioned. You follow with respect to product formation step, that is V is equal to, this is previous CSR question. Okay, V is equal to K2 into O3 into O. With respect to product formation step, rate of product formation is K2 into O3 into O. Let us consider this is equation 1. What is O here? Oxygen is whether reactant or product or intermediate. Intermediate. Here it is forming and here it is again consuming. So what is oxygen and intermediate? Okay. So to get intermediate concentration, we follow steady state approximation. So we follow steady state approximation. So from steady state approximation, how to give concentration of O? In which step O is forming? In forward reaction. In forward reaction, Y is forming. What is the rate of forward reaction? K1 into O3 by where O is consuming, the backward reaction O is consuming. What we get? K minus 1 into O2. K minus 1 into O2. Other than O we have to write. Other than O we have to write. Plus here also O is consuming, that is K2 into O3. K2 into O3. But in the question one condition is given. What is that? K minus 1 into O2 is less than K2 into O3. K minus 1 into O2 is less than K2 into O3. That means K minus 1 into O2 can be neglected. K minus 1 into O2 can be neglected. So then concentration of oxygen becomes K1 into O3 by K2 into O3. So O3 gets cancelled. So concentration of oxygen is nothing but what? K1 by K2. Now you may substitute in equation 1. So always we cannot express the rate with respect to intermediates. Always we cannot express the rate equation with respect to intermediates. We have to express the rate equation either with respect to reactants or products. We have to express the rate equation either with respect to reactants or products, but we cannot express with respect to intermediates. If in rate equation, if we are getting any intermediates, first we have to calculate their concentration, intermediates concentration with respect to either reactants or products. After that we have to substitute it. Okay. So V is equal to, we get K2 into O3 into what? K1 by K2. That means V is proportional to what we are getting? O3 power 1. So what is the order with respect to ozone? The order with respect to ozone is 1. Order with respect to ozone is 1. So in this case, if you see steady state approximation, follow steady state approximation not mentioned in the question. Apply steady state approximation to oxygen. That is not mentioned in the question, you see. Okay. So when we follow steady state approximation, if you see, if directly steady state approximation is mentioned, we can follow, right? Mention right? If steady state approximation is mentioned, we have to follow. And another one is if the condition is given like this, the condition given like that, also we have to follow steady state approximation. So some condition may be given to you. Rate of one step is less than rate of another step, okay, this type of conditions if are given, in such case also you follow steady state approximation. Since we have another method also to get rate equation, if you follow another method we will get different rate equation. So that we will see after break. Okay, take a break. Right.